Hey, Chris. Hey, Chris, it's Duncan.
Yeah, hi.
Hi, it's nice to see you after our adventures with PM and the PM and ozone.
Oh, yeah. Well, thank you for being a voice of reason in that process.
Yeah. Anyway, I'm very curious to see what you have to say today. It should be a lot of fun.
Yeah, it'll probably be briefer than the I think you were at one of the seminars I gave a few
Yeah,
months ago.
I
Yeah,
remember.
it'll be shorter than that, but you'll recognize it.
Yeah. Okay, I'm going to go on mute while I prepare my lunch.
Okay.
I'll give it just another 30 seconds here, then we'll get started, Chris. Hopefully you got a chance to squeeze in a lunch between.
Yeah, I did. Yeah,
Okay.
I've been planning this for a while.
Okay, good. Well, why don't we get started? It's about 10 to 12, and so that'll give us a time for both a presentation and a conversation afterwards. I'd like to welcome you all to our December end of the year conversation, our NHS First Friday seminars. We're thrilled to have with us Chris Frey from North Carolina State. Chris, whom several of us have known for many years, is a distinguished university professor in the Environmental Engineering Department at North Carolina State, also an adjunct professor at the Hong Kong University of Science and Technology. He's spent almost a decade on the Clean Air Science Advisory Committee, which is the group that provides recommendations to the U.S. Environmental Protection Agency on under the Clean Air Act, and he'll be talking about some of that today. But he has served both as a chair and as a member of that committee for many years. He's also been a member for several years of the EPA Science Advisory Board. And just to be clear, I should mention he was a member not associated with the Trump administration as part of the Science Advisory Board, at least for most of his tenure. He's the past president and a fellow of the Society for Risk Analysis. So he's been thinking about this more beyond, in addition to his perspective as an engineer, thinking about emissions. And to fill out, if you didn't think that was enough for him to spend his days, he's also an author and a participant in terms of greenhouse gas emission inventories in the IPCC reports on thinking about climate change and the considerations from the emissions perspective. So for any and all of those reasons, it's an honor to have Chris with us today. And today he's going to be talking about some of the issues regarding air quality science and policy in this country. So without further ado, I'll give it over to you, Chris.
Okay, well, thank you, Ed. Yeah, thank you so much for inviting me and for the kind introduction. And thanks to all of the folks at USC for hosting. And we had some nice meetings earlier today. And I appreciate the opportunity. I'm sorry this couldn't be a real visit. It would have been nice to visit the campus and see all of you in person. But so here we are. So yeah, Ed asked me to cover a couple different things. And so I think this talk will be kind of a hybrid. And I'm going to start out talking about the review process for the National Ambient Air Quality Standards, which is not my own research. And then I will segue into an overview of research I'm doing on vehicle emissions and measurement and modeling of human exposure to air pollution. And I will say I have a lot of slides, and I will probably skip some of the slides just in the interest of time. But if you have questions, we can circle back to something if I skipped it. So yeah, without further delay, let me, there we go. So yeah, I'm going to talk about these three topics, and let's get started on the National Ambient Air Quality Standard. And so this is going to be kind of some highlights or lowlights, depending on your view. It's not going to have all the details. I actually have like a 40-minute seminar just on this topic. But if you're not familiar with the National Ambient Air Quality Standards, we refer to them as the NAAQS or the NAAQS. And so I'm going to call them the NAAQS. And The NACs are mandated by Section 108 of the Clean Air Act, which requires the EPA to issue air quality criteria for pollutants that are emitted from numerous and diverse sources. And the term air quality criteria really means scientific basis for developing a standard. And these need to be regulations for pollutants that in the administrator's judgment cause or contribute to air pollution, which may reasonably be anticipated to endanger public health or welfare. And I highlighted with bold this language because I think it's a key point that the Clean Air Act does not require absolute certainty of proof beyond a reasonable doubt that there's endangerment of public health. It talks about reasonably be anticipated, which implies that it can account for uncertainty, and uncertainty meaning that if there is uncertainty but some possibility, that the agency is obligated to regulate, not that uncertainty is an excuse to do nothing. The Act also says that the standards must accurately reflect the latest scientific knowledge. So the process of developing an ambient air quality standard is given in this very complicated diagram. And it's highlighted with 3 or 4 different colors. So there's the planning stage, there's an assessment stage, and then there's a rulemaking stage. And then off on the right, there's a lighter yellow box for the Clean Air Scientific Advisory Committee, or KSAC, and public comment. So KSAC is actually required under the Clean Air Act. It's a 7-member committee by statute. It must have 1 member of the national academies. It must have 1 physician, and it must have 1 member representing state agencies. But otherwise, and actually inclusive of those members, it should represent relevant scientific disciplines. So the general process is a review. By law, the reviews are supposed to be done every 5 years. They start with procedurally with a workshop leading to a review plan that is evaluated by KSAC, and KSAC advises EPA on its review plan. And then EPA goes through a sequence of documents that begin with an integrated science assessment, which arguably is a systematic review of the scientific literature, largely aimed at identifying what are the hazards posed by a given pollutant for different endpoints, and what degree of knowledge do we have that those hazards are, that there's a causal linkage between exposure and adverse endpoints for each of those hazards. The ISA includes other issues as well, but that's kind of the central key point of the ISA. There's also a big part of the ISA on identifying at-risk populations that are most likely to be harmed, either because they're highly exposed or if exposed, are highly susceptible to adverse effects. So the point is for the external experts to review that, but because KSAC only has 7 members, it's been recognized for 4 decades. That's not enough people to review this kind of document. And so KSAC has traditionally been augmented with review panels for each pollutant and each review cycle. And those panels typically have 15 to 20 members in addition to the 7 members on the KSAC. So the panel and the KSAC will review and provide advice to EPA on whether the ISA is adequate for its intended purpose, and if not, what revisions are needed. And usually the ISA will undergo a second revision, sometimes even a third revision. That's followed by risk and exposure assessment. So based on establishing the causality and which endpoints are of policy relevance, EPA will conduct a quantitative risk assessment for the high priority endpoints. That is usually done as a separate document and actually involves a different group of EPA scientists. The ISA is developed by the Office of Research and Development. The risk and exposure assessments developed by the Air Policy Office. But these are both scientific documents, and so this also undergoes KSAC review. And then finally, after establishing the scientific foundation of adverse effect and risk, then the policy office staff develop a policy assessment, which then answers policy questions about whether the current standard is adequate, and if not, what alternative standards or new standards should be developed. And so each step of the way, there's KSAC review and there's public comment. And then once the EPA staff finalizes their assessment, then that goes to the administrator's office, and that then undergoes higher levels of review by, at the level of political appointees, including interagency review and review by the Office of Management and Budget. Okay, so I've given you a little bit of an idea of the process as it existed prior to the current administration. And then I'm going to briefly tick off 12 changes to the review process that have taken place since 2017. So in 2017, Administrator Pruitt issued a memorandum that changed the criteria for appointments to EPA advisory committees, including KSAC. So his memorandum emphasizes that members should be appointed based on geographic diversity, and not emphasizing scientific relevance, and also that there should be a greater role of government affiliated members on KSAC beyond the statutory minimum of 1. And it also, and this was the most controversial, banned non-governmental recipients of EPA science research grants from serving on EPA advisory committees. And, I don't think it's a surprise to say that, the revealed preference of this policy is to basically kick off leading scientists at the cutting edge and populate KSAC with a different type of representation that, I think can be inferred reasonably to dovetail with a policy outcome that was being sought by the administrator rather than a review focused mostly on the science. In April of this year, a U.S. District Court for the Southern District of New York found that the part of this memorandum that banned non-governmental recipients from serving was arbitrary and capricious under the Administrative Procedures Act, which applies to rulemaking processes. And however, the court did not say that that meant that the existing committees had to be vacated or that any regulatory reviews had to be redone. But it does call into question the credibility of these existing committees that were appointed under the Pruitt Memorandum. And I think for the new administration, this may be an area where the administration may want to make a correction and say, well, we would like to appoint people after rescinding this memorandum, or at least that would be my recommendation. Okay, so if we look at KSAC as it existed in 2015 for the review of the particulate matter standard, there were 6 active members of KSAC who participated. There was a 7th member who did not participate in the particulate matter review. So I'm showing those 6 as gray circles. And then there was a KSAC particulate matter review panel, which was an additional 20 people. And they represented a variety of different disciplines, which I've indicated with different colors. And, for example, most importantly, they represented epidemiology, toxicology, clinical medicine and controlled human studies, as well as exposure assessment, risk assessment methodology, air quality measurement and modeling, and other sub-disciplines important to this review. And so that augmented review panel was appointed in 2015. In October 10th, 2018, Administrator Wheeler, by press release, dismissed the 20-member KSAC particulate matter review panel. And as I mentioned earlier, there's about 4 decades of precedent for having these augmented panels. And so by removing that expertise from the deliberations and taking that away from the KSAC, and then repopulating KSAC with members appointed under a very controversial policy, it really depleted the scientific expertise needed for this review. Just to add to the list, so the 4th item on the list is replacing all 7 members of the chartered KSAC within a 1-year period. So that happened between 2017 and 2018, dismissing the KSAC PM review panel. And then on the ozone review, in July of 2018, KSAC had called for nominations for an ozone review panel, but on October 2018, EPA announced that they would not appoint an ozone review panel. So instead, after receiving criticism from KSAC itself, so even though the KSAC at this point is completely Pruitt and Wheeler appointees, the KSAC nonetheless did push back on EPA and said, you know, we missed the panel that you dismissed. We really need access to expertise beyond what's in our membership of 6 or 7 people. And could you please reappoint the dismissed panel or appoint a similar panel? And Administrator Wheeler responded by doing something that is unusual. He, instead of appointing a PM panel and an ozone panel, he appointed a pool of consultants, and number 12 consultants who could answer written questions from KSAC, but who are not allowed to deliberate with KSAC. And actually, one of the members of the pool is in the audience. So, I mean, these are expert and had useful things to contribute, but it's really, the deliberation is central to hashing out very complex scientific issues. And so the fact that it's only 12 instead of 20 for PM and say 15 or 20 for ozone, so there should have really been 35 or 40 experts, not 12. And they should have been allowed to deliberate with the KSAC and interact with the KSAC. And then some other things that were done, and I won't spend as much time on this, is that the administrators said, well, the Clean Air Act says these reviews have to be done in 5 years. So let's speed up the review process. And in doing that, they cut out some of the steps I mentioned, like they cut out the separate risk and exposure assessments. And that meant less public meetings and less opportunity for both KSAC and the public to provide input. And they also decided, well, irrespective of what KSAC wants, and by the way, KSAC, even the Pruitt and Wheeler appointed KSAC asked for second drafts of the integrated science assessment and the policy assessment, but EPA said, no, we're not going to do that. We're really focused on schedule, and so we're going to sacrifice, you know, scientific peer review for expediency. Well, they didn't say that. I'm saying that's what they did. They said they were not going to do the second draft, and that's my characterization of what they meant. So they also eliminated some of the planning documents that normally would have been done before the risk and exposure assessment. They've eliminated external review drafts. And I think one of the egregious things they did was they commingled the development of the policy assessment at the same time as the science assessment. And it had been, you know, a foundational principle of the NAAQS review to establish the scientific criteria through the integrated science assessment before developing the policy assessment. So by not closing out the science assessment, it at least opens the perception of lack of impartiality that the science assessment could be gamed to tailor to whatever messages the administrator wanted in the policy assessment. And so that at best, it doesn't look good. And at worst, it might actually be a pernicious interference in the process. Okay, so I mentioned that there was a particle review panel that was appointed in 2015 and dismissed in 2018. By the way, that panel was dismissed just 5 days before the integrated science assessment was released for public review. And so I was a member of that panel, as was Dr. Rob McConnell, who's in the audience. You can probably pick him out somewhere in the picture. He's actually in the foreground of this picture. We, as a panel, decided that we were not happy with being dismissed, and we collectively agreed that we don't have to be appointed by EPA to continue our public service of advising the agency and the public on the scientific foundation of the PM NAAQS. And so we elected to proceed with reviewing the integrated science assessment and the policy assessment. And in fact, we submitted consensus reports to the EPA with our advice on those two documents, and also on the broader charge questions that EPA had given to the remaining KSAC regarding whether the current standards are adequate to protect public health, and if not, what revisions are recommended. So in this particular photograph, we had a face-to-face meeting. This is in October 2019. We met in the same hotel where KSAC usually meets outside Washington, D.C. We had a meeting manager who's the former director of the EPA Science Advisory Board staff office, who did a good faith ethics review of all of our members. And we conducted the meeting according to the same rules under the Federal Advisory Committee Act that KSAC is supposed to operate under, in terms of the various procedures of how the committee operates. And one of the key principles is all of our deliberations were in public, and we also accepted public comments at our meeting, and we produced a document that's in the public record. And by the way, there's actually a 2-day video of this meeting if you would like to watch 15 hours of a committee deliberating on PM standard. That's available on YouTube. So this is the membership of our panel. There's 20 members. This is the roughly the same membership that the panel had before it was dismissed. There were a few other people who, for various reasons, didn't participate, not because they didn't support this, but just because of concerns about retaliation, to be honest. So anyway, we all stuck our necks out and just continued with this review. So anyway, I'm very proud to be part of this committee. I ended up becoming chair of the reconstituted independent PM review panel. I think that's because I probably had more time to do that than anyone else did. And but it was a lot of hard work by everyone on the panel. This panel worked harder than any panel I've ever been on. So I don't have time to go into a lot of details on our findings, but I'll highlight a few key things. So one of our findings is about the causality determination of the relationship between annual and 24-hour exposures to fine particulate matter and premature death. And our finding is that there is consistent epidemiologic evidence augmented from multi-city studies, augmented with evidence from single city studies at ambient concentrations that are comparable to current air quality and below the level of the current standard. And that the epidemiologic evidence is supported by research from experimental models in animals and humans, and by a small but growing number of accountability studies, and that there's a causal biologically plausible relationship between ambient concentrations below the current standards and adverse health effects, including premature death. And we wrote a very long report that we have about a 200-page report that goes into more detail on this and other issues. With regard to that, so that was our key science advice. With regard to our policy advice, or our science advice regarding the current standard. So we found that the current fine particle annual and 24-hour standards are not protective of public health. I won't go into what I mean here by indicator, averaging time, and form. Those are some of the ways that the standard is defined. But if we focus on the level or the annual concentration, the current standard, annual standard, is 12 micrograms per cubic meter. And we recommend it be revised to no higher than 10 micrograms per cubic meter and as low as 8 micrograms. And then for the 24-hour standard, which is currently at 35, we recommend it be revised to no higher than 30 and down as low as 25. And the idea of the high end is that at those levels, it would be protective of public health, but at the lower levels, it would provide more margin of safety. In other words, it would be more protective of highly sensitive subgroups, either because they're highly exposed or highly susceptible. Now, the idea of margin of safety in the law is a policy judgment reserved to the EPA administrator, not for a science advisory committee, and that's why we gave ranges here. So in April of this year, Administrator Wheeler released his proposal for the fine particle and the PM NAAQS, which includes fine particles and other particle standards, but I'm just going to focus on fine particles here. So he concluded that the associations observed from the epidemiologic studies, quote, without supporting evidence at similar PM 2.5 concentrations, without supporting experimental evidence, leave important questions unanswered. And I'm not sure I understand what this really means, but I think what it means is that Administrator Wheeler wants to see controlled human studies for the same concentrations and averaging times as the current standard. And that would mean an annual exposure to 12 micrograms per cubic meter in a controlled human study, or a 24-hour exposure at 35 micrograms per cubic meter. And others in the audience are much more expert on controlled human studies than am I. But, by the way, controlled human studies for fine particles are sub-daily, typically only a few hours, and they can only really address healthy adult subjects for these very short exposures because there are ethical concerns about causing permanent harm to subjects at longer exposure concentrations or for subjects that have pre-existing medical conditions who would be more adversely affected by such exposures. So the administrator seems to be asking for something that is either unethical or just impractical. And then likewise for animal studies, those studies are usually run at higher concentrations to observe effects in a shorter amount of time. The sample size needed to observe effects at concentrations comparable to the level of the current standard would be likely on the order of hundreds of thousands, if not millions of animal subjects, which would be prohibitively, ridiculously inexpensive and implausible. So in my view, this is my personal opinion, the administrator is creating a burden of evidence that is not required under the law. The law says to look at anticipated effects, not absolute certainty of proof. And then is postulating these absurd requirements. There's other text here, but in the interest of time, I think I won't go into all the details on the slide. But the bottom line is the administrator is overemphasizing uncertainties and downplaying the consistency within the epidemiologic studies and the coherence between epidemiology and the experimental studies that are available, and just generating doubt. And that's a well-known denial tactic. Also omitted in the administrator's rationale is no mention of all the ad hoc changes to the review process that I mentioned, barely any attention to at-risk populations, barely any attention to environmental justice, no explanation of why it's appropriate to interpret uncertainty as denying effects rather than considering them as related to anticipation of effects as required under the law. And also there's a step that usually the EPA staff do, a provisional assessment of new evidence since the ISA was completed. And most notably in the last few months, Harvard has released a new study that is a causal analysis of its 2017 Medicare epidemiologic study that uses some causal techniques that the current KSAC has been complaining were omitted in prior epi studies. And the causal reanalysis of that study basically confirms what was found in the earlier 2017 study. So anyway, there's a lot of detail, but in the interest of time, I won't go into all of that. I will say our panel, we kind of formulated a shorter version of our advice that we have published in the New England Journal of Medicine as a sounding board article that kind of summarizes the bottom line of all these issues that I just mentioned to you. So if you're interested, you may want to read that. So the status right now is the particle standard is under final review at the Office of Management and Budget. And it could come out any day as a final rule. I think everyone generally expects that this administration will promulgate a final rule before the end of the current term. And then that will put in place a PM standard that inadequately protects public health. On the ozone side, which I haven't talked much about here, but The ozone standard has been reviewed, and EPA has issued a proposal to retain the current standard. The controversy there is the process deficiencies that I mentioned. And also for ozone, my view is the administrator has not given enough attention to at-risk populations. That may or may not mean that the rule should be revised. I think the scientific evidence is not as strong that the rule needs to be revised, but there is some hint, if you look at anticipated effects, that there might be some rationale for considering alternative ozone standards, which was not done by the SCEHSC or by the EPA administrator. I think for both of these rules, EPA will be sued. The question, especially for PM, which I think is the more salient one in terms of public health, how quickly can a new administration restore a science-based rule? And I think some of this will depend on the particulars of how the courts intervene and what latitude the courts give to EPA to maybe repeat some of the steps and reconsider the current standard, or will the courts require wholesale starting from the very beginning, in which case then probably it's better to just start a new review cycle, but that might delay for 4 or 5 years before we see a revision that's actually protective of public health. So I think right now there's a lot of uncertainty about what that outcome will be. Okay, so having talked about that, I'm going to segue to areas of my own research. And I'm going to start by talking about vehicle emissions. And I don't think I need to convince this audience that vehicle emissions have implications for public health. There's not a lot of studies that specifically apportion health risk, for example, to on-road transportation. But here's a couple of studies that look at global premature death from exposure to on-road transport, fine particle emissions, and estimate roughly 200,000 people per year globally die prematurely as a result, with fairly high numbers even in the US and certainly in China and India and many other countries. So some of the questions I've been interested in is how do we measure the real world energy use and emissions from transportation? Much of the emissions data has been based on laboratory dynamometer testing, which involves very rigorous scientific instrumentation, but does not involve representative operating conditions for the vehicles. And so, although it's highly precise and accurate for the lab condition, it may not be accurate with regard to what's happening in the real world. And so what are the key sources of variability in the inventory in the real world? And what are the trends in fuels and technology and so on that are affecting those emissions, and how effective are policy instruments such as emission standards in controlling emissions? So I've been looking at these questions using portable emission measurement systems, where we collect data on vehicle location that we can tie it to infrastructure like road type, the vehicle technology and fuel. We sample different kinds of vehicles. We can look at the dynamics of vehicle operation, which are related to driver behaviors. We can look at ambient conditions, fuel use, and emission rates. And so we quantify this based on real world operation. These are examples of some of the portable instruments that are used, and they vary in terms of their precision and accuracy. The one on the upper left is what's called a 1065 compliant instrument. So this actually can be used for regulatory applications. The other instruments are not regulatory instruments. This one is called a simplified PEMS. It uses slightly different detection methods, but it's a smaller, lighter instrument. And it does not use an exhaust flow meter, which is required on this instrument. Instead, we calculate exhaust flow based on measuring or logging some engine variables like engine RPM, and from that we can infer mass airflow and fuel flow and airflow. This is a newer instrument. It's a very small instrument. This dimension here is about 10 inches, just to give you an idea of its size. And so this is what's called a micro PEMS, and you know, there's a recognition that there's some niches of, you know, where we just want real world data. We're not trying to do a regulation or a certification. We're just trying to get representative emission rates. And it's better to have less expensive, smaller, more portable instruments that we can use more widely to instrument more vehicles to get a larger representative vehicle sample than it is to have an expensive instrument that can be used on fewer vehicles that is a less representative sample. So, you know, there's a trade-off between the precision and accuracy of the instrument and the resources needed to use that versus lower cost instruments that can allow you to get data under much broader, more representative operating conditions. So we've done a lot of measurements for actually about 20 years now. Most of the things I'm listing here are from the last decade or so. And we've done work on road vehicles, both light and heavy duty vehicles, as well as construction vehicles and locomotives. You know, we also have done a study on snowmobiles in Yellowstone National Park. I don't list that here. So this is what an instrumented vehicle looks like. And the main thing you see is a hose from the tailpipe going into the window, and the portable emission measurement system is in here. And then we have an ambient air intake, and here's exhaust air coming out of the instrument. And we used to put a magnet on the car that said there was an emission test under progress, because we thought people would wonder, why is someone driving with an exhaust hose going into the vehicle? Like, is this a suicide mission? And one time I have been pulled over by the police because I had an instrumented car, and I was taking my daughter to middle school in the morning. And I saw another driver who was taking their child to the same school. And it turned out that driver called the police because they were concerned I had kidnapped a child and I was trying to kill them. And then I told the police, no, I'm just collecting emissions data on the vehicle. And they said, oh, fine. And they just walked away. So anyway, so we don't put the sticker on anymore. So this is the kind of data we collect. We collect data on the gas concentrations, engine sensor data, GPS data, weather data. And so we're simultaneously collecting second by second data on a lot of different variables, typically over 3 to 10 hours per vehicle. And so we have to time align the data, do quality assurance on the data. So we've developed procedures for that. I'm going to show some example results based on measurement of light duty vehicles. And over a period of the last 12 years, we've measured about 230 light duty vehicles on the same set of routes, which I'll show you in a minute, in the Raleigh, North Carolina area. So this is just a frequency plot of the model years that we've measured. So 97 to 2019, engine horsepower from about 100 to 400, curb weight from about 2,000 to 6,000, and accumulated mileage. We measured a vehicle that had 300,000 miles, but we have a pretty wide range of these characteristics. And, you know, we've also characterized the fleet in terms of make and model. And, you know, while it's not proportionally representing the on-road fleet, we represent really all the key segments of the on-road fleet in terms of the different manufacturers, the different types of vehicles like sedans and SUVs and pickup trucks, and so on. So I think we have a pretty robust sample. And then for each vehicle, we drive it on 110 miles of this network that originates at NC State. And then we drive from NC State to North Raleigh. And these are typical commuting paths. So North Raleigh is kind of a residential area, and NC State is near the downtown of Raleigh. So these represent commuting routes from residence to a business district. And then also we look at from North Raleigh to Research Triangle Park, which is another central business district. And that's a different kind of commute. It's a longer commute on different road types compared to the commute to downtown. So we represent a variety of road types, speed limits, traffic control, you know, signalized intersections, roundabouts, freeway ramps, and so on. And so we actually, the paper cited here, we did a lot of work to figure out what routes to sample to get a good statistical representation of variation in power demand of the vehicle. And then we quantify power demand as vehicle-specific power, which is a function of speed, acceleration, and road grade. And I won't go into all the details of this equation, but the terms represent, this term is the change in kinetic energy. This term is the change in potential energy as the vehicle climbs or descends hills. This term has to do with rolling resistance, and this term has to do with aerodynamic drag. And so those are the main physical resistances that affect the attractive power demand for the vehicle. And we and others have shown that this is very linearly related to fuel use of a vehicle. So it's a very good predictor of fuel consumption. And it also turns out many of the emission rates are proportional to VSP, even though they're not linear with VSP. So in some early work we did for EPA back in 2002, we developed a modal modeling framework based on VSP, where we divide VSP into ranges, and our mode 3 includes idle, modes 1 and 2 include deceleration, and modes 4 through 14 include various levels of positive power demand, which can represent high-speed cruising or acceleration, depending on the mode. So this is just a summary from all of our data. So we have 232 vehicles. Each of them we have about 3 hours of second-by-second data. And when we put all that data together, this is the average modal rate for CO2 emissions versus the VSP, vehicle-specific power mode. So mode 3 is idle. Usually that's the lowest rate. Negative VSP means deceleration. Usually that's a little higher than idle because the engine's running at elevated RPM during deceleration. So it's not running at idle RPM if there's an automatic transmission. And then we have increasing CO2 emission rates with increasing positive VSP. And it's a fairly nice linear relationship with CO2, which is what we expect. With carbon monoxide, we see a very nonlinear relationship, and this is expected because of how catalytic converters are controlled. At very high power demand, they can overheat because there's such a high flow rate of carbon monoxide out of the engine. So at high power demand, they are intentionally defeated to some extent to prevent overheating the catalyst. And that's why you get such high CO emission rates at very high power demand. And then it's a little hard to see. This is a slightly nonlinear relationship for hydrocarbon. And there's kind of a nonlinear relationship for NOx. It looks linear here, and then it kind of has an inflection point and is more sensitive to VSP at high VSP. So the main nice thing about the modal model is we don't have to fit an analytical function, and the data will reflect whatever's the underlying trend, and it does not have to be linear. So we can look at different real-world driving cycles in terms of the distribution of time in these different modes. And just as an example, Route 1 here is a freeway route. Route A is an arterial. And not surprisingly, the freeway route has a higher proportion of time in mode 12, which is a high power demand mode, than does an arterial route. And those differences, although they might look small on this graph, because the emission rates are so high at those high VSP modes, they do have a significant effect on cycle average emission rates. And so this is how we can account for sensitivity to real world driving with these real world based models. So we've done lots of different studies, and I don't have time to even read this slide, so I won't try to do that. But one of the things that in my work I've tried to demonstrate is you can tailor these real world studies to different study objectives. And some of them, could be looking at technology assessment or assessing different fuels or assessing different traffic control and so on. So there are lots of different ways you can design these studies. This is one of our early data that one of the first data we collected like almost 20 years ago. And this just illustrates a key point. At that time, based on existing vehicle emission models, if you ask people about what would cause high emissions, most everyone would say, oh, well, this low speed stop and go driving is, that's really bad, and that's got to have high emissions. And so, we think this is where the emissions are. And there were some reasons why people thought that. It had to do with the ways that laboratory dynamometer data were extrapolated in one of EPA's earlier emission factor models. And that extrapolation led to actually a very misleading implication of extremely high emissions for stop and go driving. Well, it turns out when you measure this, so here's the second by second speed. If we look at second by second emission rates for that same trip, every time there's an acceleration, there's a little bit of an emission peak, but it's that acceleration to 45 miles an hour that really dominates the emissions of that particular trip. So it's not really the stop and go part of the stop and go driving that's the problem. It's the go part when you finally get out of that delay that is the problem. And so if you wanted to mitigate emissions for this trip, you'd want to mitigate this last, burst of acceleration to get through this bottleneck. Or you'd like to smooth out this trajectory. Okay, and so we also looked at, the relative proportion of different driving modes to the trip emissions. And, what we show here, this is for a typical commuting trip in our area, that although acceleration is only, about 10 or 15 or 20% of the trip by time or distance, it can be between 40 and 60% of the emissions for that trip. And so, mitigating situations that produce especially excessive accelerations would go a long way toward lowering trip-based emissions. And we have done some studies that look at that empirically. This is another way of looking at the data. This is looking at the effectiveness of emission controls, and we're looking at modal NOx emission rates for Tier 1, Tier 2, and Tier 3 emission standards. And what this shows is, what we expect and we hope to see is that, the higher tier emission standards, which are more stringent, have lower real world rates than the less stringent earlier standards. And that's not a given thing. I mean, in Europe, there's plenty of evidence for diesel vehicles that that's not happening in Europe. But the US fleet is largely gasoline for light duty vehicle. And so we don't have quite the same non-compliance problem that there is in Europe for the light duty fleet. Although we do see that with diesel light duty vehicles in the US, but they're just a small part of the US fleet. We also looked at, and this is a paper we did a few years ago, on how do real world emissions compare to the emission standards on a cycle average basis. And this is looking at Tier 2 vehicles. And here we're looking at what's called the certification level. So that is the measured value in the dynamometer test that the vehicle's certified to. And what we found generally is the real world emissions are higher than the lab-based measurement that the vehicle was certified based on. But the certification level is usually lower than the standard. In order to get compliance with the standard, the manufacturers usually design the vehicle to do better than the standard in the lab test. So there's a little bit of margin. So what we find is generally the real world emissions are maybe less than or comparable to the standard, but the real world emissions are higher than the measured value during the compliance test to verify that the vehicle meets the standard. So it's a bit of a complex story, but sort of the good news is that, that means the US, not just the emission standard, but the enforcement program is reasonably effective, at least for light duty gasoline vehicle. We know that's not true for diesel, and that's very famously illustrated by the VW scandal. Okay, and then I think the last vehicle thing I'll mention is, if we look at the second by second signals, we find that a very small part of the trip produces a lot of the emissions. And we've been looking in the last couple of years at, based on all of this data we've collected, we have enough data now to obtain statistically stable estimates of the spatial variability of emissions on our measured network. And so here we're looking at emissions hotspots for nitrogen oxides in red, and then the cooler colors represent lower emissions. And I've circled the top 10 highest emission segments on this route. And we can attribute this to various vehicle activity metrics that might predict why these emission hotspots are occurring. And that's a subject of some ongoing papers we're working on. But it turns out that the hotspots are not the same for different pollutants. So if we look at hydrocarbon, what we'll see, I'll show these same 10 locations, and you'll see some of them are not hotspots for hydrocarbon. And there's some hydrocarbon hotspots that are not hotspots for NOx. So here's hydrocarbon, and then the circles represent the NOx hotspots. And here we see hydrocarbon hotspots that are at different locations, and NOx hotspots where it's not a hotspot for hydrocarbon. So the point being, not surprisingly, that the hotspots vary by pollutant because different pollutants are sensitive in different ways to the vehicle dynamics during operation. And one of the things I want to do in the longer run is develop, validate that models could predict these hotspot locations. And we have a draft paper not yet submitted where we've done that. And that we could better link at high spatial resolution vehicle emission hotspots with near road air quality hotspots, and then assess the implications for exposure. So I think with that, I'm really almost out of time, but I don't have time to go into the exposure part in detail, but I do want to just show you, I'm going to skip a lot of stuff here, but I do want to show you just a little flavor on the exposure side. That one of the current projects I'm working on is to develop an exposure simulator for Hong Kong. And this is part of a large multi-institutional study based at the Hong Kong University of Science and Technology, where we've collected microenvironmental data with portable instruments for about 200 different locations, representing roughly a dozen major microenvironments in Hong Kong. And we're developing a cell phone app to allow individuals to track their personal exposure. But in parallel with that, I'm developing a standalone estimator of population-based exposure to use for policy planning and evaluation. And so we're basing this on EPA's APEX model, which is the same model used in the risk and exposure assessments for the National Ambient Air Quality Standards. But we're calibrating it with local data for Hong Kong for air quality and population, microenvironmental infiltration, and activity patterns in terms of time location diaries for individuals in Hong Kong. And we've just recently calibrated this model and got it to run. We run this very complicated case. I don't have time to go into the details here, but I just wanted to show you a kind of the results that we get from this. So here we're quantifying the ratio of exposure to ambient concentration for fine particles in the winter and summer. So this is essentially the relationship based on infiltration from outdoors to all the microenvironments. And this is based on the population weighted mixture of how much time is spent in different microenvironments by different people. And these distributions are based on hourly estimates for 5 days, 5 weekdays of 50,000 individuals. So there's about 6 million person hours represented by this curve. And so each point on the curve is one person being exposed for 1 hour. And so in some hours, people are outdoors, so their exposure to concentration ratio is 1. For some people, they're in an office with a HEPA filter ventilation system, and they have very low exposures. Some people live in a home with the window open. Their exposure is probably 70 or 80% of the ambient exposure, and so on. So, we account for the population weighting of and time spent in all these different microenvironments. And then we're doing this for other pollutants. So we're doing a multi-pollutant exposure assessment, and the infiltration and exposure to concentration ratios are quite different for different pollutants. And also we're looking at, for example, different demographic groups like children, adults, and older adults who spend time in different types of environments. Adults spend more time in office. Older adults spend more time at home. They have different ventilation characteristics. So there's different exposure to concentration ratios, which are more pronounced for some pollutants like NO2 than say for ozone. But anyway, these are the things we're looking at now. And I guess more generally, I don't have time to cover it, but I'm really interested in the linkage between vehicle emissions, in-cabin exposure, near road exposure, infiltration of transport emissions into nearby microenvironments such as homes and schools and so on. And part of the theme of our work in Hong Kong is to move toward a new paradigm in air quality management, where in the 70s, a lot of air quality regulation was focused on just controlling emission sources based on technological capability. And then, where you are in Southern California, you're at the epicenter of, the scientific revolution that, developed insight about, ozone formation and the complex physics and chemistry in the atmosphere that led to the development of a scientific foundation to look at the relationship between emissions and air quality, and therefore to focus on managing air quality and then go backwards and control emissions to achieve air quality goals. And that's led to tremendous health benefits, such as through the National Ambient Air Quality Standards. But the next logical step would be to manage personal exposure. And that involves ways of managing your exposure beyond just managing ambient air quality. And one of the goals of having our app to go to individual people is to inform them about the choices they might make to manage their own exposures. So this is my last slide, I promise. So on the first topic, the NAAQS review, there's a need to restore the quality, credibility, and integrity of the review process. On the other topics I've talked about, advances in measurement methods for vehicles, but also for exposure, are enabling collection of more representative real-world data for larger sample sizes. And that's providing important new insights regarding spatial and temporal variability for emissions and also for exposure. And I think this creates new opportunities for designing field studies to take advantage of those capabilities while helping support health-based scientific studies and also help policymakers with making decisions. And then, I also see an important role for these kinds of empirical data to develop, calibrate, and validate, new generations of modeling tools to put this power literally in the palm of your hand in a cell phone app, as well as in the hands of policymakers. So thank you very much for indulging my slightly long seminar. There's a lot more I'd like to tell you about. If you have any questions, feel free to email me, and I'm happy to take any questions as time allows.
Okay, thank you very much, Chris. So the floor is open for any questions that come from anybody, and I think I'm not sure whether you want to try to raise your hand or just sort of blurt out a question. We just sort of see how we manage that. So anybody's got a question to start, please, we're ready to go.
Well, I guess you've already partially answered this, but do you have sort of any idea of what the new administration is going to do with EPA, both in terms of the kinds of process things that you talked about, as well as whether there's anything they can do to reverse a standard that's already been promulgated just before they leave office?
Yeah, it's a good question, and I don't have the insider answer. I mean, I've talked to some people about ideas for this, but I can tell you my opinion of what they are likely to do, but that's just my opinion. It's not a representation of the new administration. I think that my impression is they are concerned about the membership of the advisory committees, and I think that may be one thing they would take on early is, they could rescind the Pruitt memorandum I mentioned, and then I think they could take a position of, we thank members for their service, but we want to correct the appearance of lack of impartiality from those appointments and begin a new nomination process. But that will take time, and that will take at least 6 months to go through that whole process, and maybe longer. So that won't fix things immediately. But it would be good on the PM NAC side. I think that there are several options. And some of this, as I mentioned, depends on how the courts intervene. You know, if a court were to say, well, so just as context, so EPA does not have to follow KSAC's advice, but if EPA diverges from KSAC's advice, they have to provide a rationale. And I think the new administration could take a legal strategy of really not defending the expected final PM NACs. So it'll go to court, and then I think EPA could readily agree to reconsider the standard, or readily agree to vacate that standard, or to a remand where it essentially would redo the analysis. But those would have different implications in terms of the schedule. I think if EPA could reconsider the standard, they can build on the current ISA and the current policy assessment. That's a little tricky because, you know, many of us, me included, have been arguing there are lots of flaws there. But I think one thing our panel felt comfortable with is, even though there are flaws in the ISA, and it would have been nice to see a second draft, the scientific evidence is sufficiently clear that it's not necessary to have a second draft for us to have developed our advice, and we went ahead and developed advice on that premise. Now, I don't know to what extent the court would defer to our committee, because we are not an official governmental panel, and so that's a whole other set of question marks. But I think we did provide a rationale for EPA to refute the scientific findings of KSAC, and at least show the court, here's a rational basis for why we're not following KSAC's advice. And therefore, we would reconsider the administrator's rationale. That would be the quickest way, because then all of that is at the rulemaking stage. But if the courts would require EPA to go back to KSAC, then I think first it would be important not only to have an appropriately appointed KSAC, but to have an appointed PM review panel. And that can be done in the same time it would take to appoint new members to KSAC. So, but again, I think that's roughly 6 months, maybe a little more. There is precedent for KSAC to reconsider an existing decision. For the 2008 ozone standard, Lisa Jackson, the administrator in the first Obama term, had asked KSAC to reconsider its advice on the 2008 ozone standard. And that was heading toward a quicker rulemaking process than waiting for a second 5-year cycle. But President Obama intervened and just put a stop to that. So we don't know whether that would have worked or not, but that's another possibility. But I think even that would take probably at least a year, probably more realistically a year and a half. So, I mean, I think the best case is it would take maybe a year and a half to get a correction to the standard that is promulgated. And the worst case is EPA would just have to start over with a new review cycle. And then there's a question of whether they could even get that done within a 4-year term under the new administration. So yeah, that'll be kind of touch and go, and so I think it really all depends on the courts.
Well, I was glad to hear you say that despite the flaws in the science assessment and the policy assessment documents, that they're a basis, that they still provide a basis. And I have to say, I was impressed with the career EPA scientists that had to pull that together. They're not the problem. The problem is with the administration. And
yeah, absolutely. Well, yeah, and actually that was, I didn't put it in this talk, but that was the first thing we said on our independent panel. The first thing we said was to appreciate the staff. Yeah, they really were courageous and honest.
Just hope they survive the next purge.
Yeah. So, yeah, there was something else I was going to say, but now I forget what it was.
I'll let other people ask questions.
Yeah. Thank you.
So thank you. Other questions from the audience? I have a question for you about some of the mobile on-road measurements that you've been working on. And you said it made some, you tried to reflect the fleet and get some sense of what it is, even though you've done a couple hundred vehicles. I mean, here in California, we have an annual smog check by which you either have to sort of bring your car in or else can't re-register it. I don't know if they have a similar system in North Carolina.
Not anymore, no.
But I was interested in, here in California, because of the weather, we tend to have older vehicles on the road for longer periods of time. And so the turnover of the fleet is an issue of sorts. I was wondering, how you sort of factor all that in North Carolina, trying to get some sense of what the vehicles that even the basic question of what the vehicles are that you do. Do you use staff vehicles? Do you get volunteers? Do you go out and purchase vehicles? How do you get the vehicles that you use to evaluate?
Well, we don't purchase vehicles. We don't have budget for that, but we do. So we've used research team member vehicles. We have rented vehicles. We also so every year, except this year, I haven't done it, but I teach an air pollution control class every year, and I include a kind of an optional project where if students would like, they can volunteer their vehicle for measurement, and so we collect data. So actually, most of the vehicles that we've measured have come from that. And what I've been kind of impressed by with the student volunteered vehicles is, and this relates to the demographics of our student body, is some students have really new vehicles and some have really old vehicles. Like the 300,000-mile vehicle was a student vehicle. But I mean, we see a really wide range of student vehicles, many that are much nicer than any car I've ever had. And, many that remind me of the car that I had when I was in college. So, but yeah, but nonetheless, we do try to benchmark, as I alluded to, the distribution of the sample we have to various metrics of the real world fleet. And as I said, it's not a proportional sample, but it is, if you stratify it into the subgroups, we represent each of the key subgroups pretty well, I think. Yeah, and as far as the older vehicles and how those are represented, I mean, that's just a matter of, if we were to use this in a model, what weight we give to different model years in the vehicle distribution. So that's kind of easy to account for in a modeling framework.
All right. Thank you. Other questions from the audience?
Maybe I can ask a quick question. Hi, this is Rima. Chris, thank you. This was fascinating. I'm wondering about what you said with the intersections work and the hotspots for emissions, and how, like you said, not surprising, maybe the NOx versus the hydrocarbons versus etc. are slightly different in space. Do you have thoughts for maybe kind of modeling like all these pollutants as a mixture in a way, or doing some kind of source apportionment using all the pollutant data and mapping those factors in terms of where the hotspots are occurring? Because I'm trying to think that maybe there are, maybe several pollutants will come out more associated with a specific process that happens earlier in the acceleration or later, etc. Meaning that maybe all these pollutants and the way they're showing up are not necessarily completely independent. And hopefully,
right, yeah. Well, they're definitely not independent, but they are differently sensitive to, causal factors in high emissions. So, I guess the short answer to your question is, I mean, kind of yes. I mean, we haven't done like a weighted combination of multiple pollutants as a single index, but we do look for kind of common causes across the pollutants. Of course, in some sense, just from a research perspective, it's more interesting when we see the heterogeneity. So we've kind of focused on that for the moment, and trying to understand, like, so why is this location a hotspot for NOx, but it's not a hotspot for hydrocarbon, or vice versa? And so we kind of been more thinking along those lines. But I mean, I think if you looked at a mixture of pollutants, you know, you'd probably find more stability in where the hotspots are, and that might actually smear out the signal a little bit, where it becomes, you know, if you have a mixture of things, sometimes, you know, if you look at it in isolation, you can see a clear reason why, but when you mix them together, it's then ambiguous why that would happen. You know, it's like if you have two models and one model predicts this and one model predicts that, and you take the average of them, neither model supports that outcome.
Yeah.
And so I wonder about that kind of problem in attributing some kind of weighted hotspot. But yeah, it's an interesting question. And I think, you know, part of the challenge is it also begs the question of what's the right way to weight those pollutants. And, you know, I would think some kind of health-based weighting would make sense, but I don't think there's a unique answer to how to do that. So, so then it also raises the question of how much of a problem do we introduce by trying to weight them?
Yeah, I mean, I think I was thinking of latent processes in a way, but I completely agree with you. And trying to think of what you said also about getting to, let's say, exposure prediction or how you might predict those patterns. It's definitely a tough problem. So, but very interesting. Thank you.
Sure.
So I think that's about almost all the time we have, unless there's a quick question from someone. I want to thank you, Chris, for sharing with us a wide range of interesting research and ideas and thoughts for us. We will continue after a short break to have a discussion with you now as we switch another hat yet again, think about climate change and talk about that at 1:30. And so thank you to all those who attended. Wish you all a good holiday season. For those looking forward to January, in January we will have as our speaker Mark Berman from the University of Chicago talking about some of his research in neuroscience and thinking about some of the issues associated with exposure and effects on the brain. And so thank you, Chris. Thank you all.
Oh, you're welcome. Thank you.
And we will see you soon. Take care.
Okay. Thanks, everyone.